तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Values of the total angular momentum quantum number of the electron are 3 halves and 5 halves. I have not proved this, but I made the statement that if you took two angular momenta J1 and J2 and defined that to be the total angular momentum, then this quantum number, if it is denoted by J, the corresponding quantum number for capital J, then this J runs from modulus J1 minus J2 up to J1 plus J2. I did not prove this statement, but it is easy to see that it is plausible from the rules of what happens when you take the raising operator and act on stretch states and so on. But in the present instance, for an electron, L plus S is the total angular momentum J. This quantum number is L. That quantum number is always a half. The spin of the electron is a half, and therefore if this L is 2, then the only allowed values are 3 halves and 5 halves. So this statement is true. Okay. What happens if L was 0? If you were in the S state of the electron in an atom, what happens then? The only allowed value is a half, because you have to take modulus J1 minus J2, so the only allowed value is half. Then the total angular momentum is in fact just the spin angular momentum of the electron. Okay. As you know, in the hydrogen atom, which I have assumed you have actually studied in the chemistry class, the states of the system for a hydrogen atom, the states of the electron are specified by a principal quantum number n, which takes on the values 1, 2, 3 ad infinitum, and then an orbital angular momentum quantum number L, and this L runs over the values 0, 1 up to n minus 1. So when n is equal to 1, you have only the possibility L equal to 0, so you have the 1s state and then the 2s, 2p states and so on. The magnetic quantum number m, which is the quantum number corresponding to any component of the orbital angular momentum, this takes on values from minus L up to plus L in steps of 1, in steps of unity. And then there is the spin quantum number, and of course we know that the spin quantum number S is always a half, and the projection, let me just denote it as m sub S, therefore is equal to minus half and a half. These are the only two possibilities. And now you could ask what the degeneracy of the electron is when it is in a given state with n, L, m etc., in a general state with principal quantum number n, and that degeneracy factor Gn, it so happens that for the 1 over r potential, the Coulomb potential, the energy levels depend only on n and not on any of these quantum numbers, unless you break the degeneracy by including some other interaction. For instance, you put a magnetic field, you switch a magnetic field on, that will couple to the spin of the electron, and then there is a magnetic potential energy minus mu dot b, and that will distinguish between plus half and minus half for ms and so on. There are other factors which I will come to, other features which will also tell you that the quantum numbers, the energy levels could depend on L, m etc. In a minute, let me get to that. But if you do not have any of that, then this Gn, since En, m and the other quantum numbers is equal to a function of n alone for the hydrogen atom, it is actually minus 1 over n squared in Rydberg units. Therefore, this Gn is equal to the number of possibilities over m sub s, equal to half minus half up to plus half times 1, because that is the number of possibilities you are counting, the number of possibilities for m equal to 0 minus L up to plus L, and then you have to count the number of possible values of L from 0 to n minus 1, and this is equal to Gn. This straight away gives you a factor 2, so this is equal to twice. This gives you a 2L plus 1, so you have to sum summation L equal to 0 to n minus 1 2L plus 1, and this is equal to 2n squared. Okay. So that was asked separate question, and that was in fact in one of the fill in the blanks. It said the degeneracy of the electron in a hydrogenic atom is G sub n, taking into account the spin is 2n squared. If you did not take the spin into account, if you ignore that internal degree of freedom, then it is just n squared here. Now if you switch on a magnetic field, the following is going to happen. There will definitely be a coupling between the intrinsic magnetic moment of the electron and the external field that will break this degeneracy in m sub s. And then if you have anything, any potential which is not central, then there is also a dependence on m, because if it is not central, if it is a central potential, no axis in space is distinguished from anything else, and therefore there is degeneracy over m. In general, if you had a central potential alone, V of r, which was not a Coulomb potential or some very special potential like the harmonic oscillator potential, but an arbitrary general central potential with no special symmetries whatsoever, then what would the degeneracy be for a particle of spin half? There is a factor 2 which comes from the spin, but over and above that there is a degeneracy in m. So in such a case the energy levels would be a function of n as well as L, and what would be the degeneracy of each of these states for a given n and a given L? 2L plus 1, just 2L plus 1. All the m values would give you exactly the same energy, just 2L plus 1. If you included spin, it is twice 2L plus 1 in that case. Now what happens in practice, even in the hydrogen atom, is that there is an extra contribution called the spin orbit coupling. There is a coupling between the spin of the electron and its orbital angular momentum in the following sense. It is actually a more complicated effect, but it is as if, pretend for a minute that you are on this rest frame of the electron. You still have an intrinsic angular momentum S or a magnetic moment. You see the proton going around you, which is a current loop, and therefore there is a magnetic dipole moment associated with the orbital motion, and that will be proportional to the orbital angular momentum, the magnetic moment, which is L, and therefore there is going to be a term in the Hamiltonian proportional to L dot S. So you have, that is called LS coupling, and the moment you have this, or spin orbit coupling, and the moment you have an L dot S coupling, you have broken the symmetry which the Coulomb potential has. Therefore the energy levels become dependent on L. In other words, this accidental degeneracy, that this does not depend, these energy levels do not depend on L, is gone now, and there is in fact a difference in energy between the different L states for a given n, and that is the reason why the spectrum of the hydrogen atom looks like 1s. This corresponds to n equal to 1, L equal to 0. I am ignoring now no external field, and therefore no dependence on the spin at all, and then there is a 2s state and a 2p state. This corresponds to n equal to 2, L equal to 0, n equal to 2, L equal to 1. these states are split. They would not be split if you did not have a spin orbit coupling, both these would have exactly the same energy. And then of course there is a 3s, 3p and a 3d state and so on, and they are all split because of spin orbit coupling. As this coupling the effective split is extremely small compared to the actual energy value of either the eigenvalue of either the 2s or the 2p state. There is a small splitting, but as you go up in the periodic table and as the atomic number increases, as the z value of the nucleus increases, it turns out that the spin orbit coupling becomes more and more prominent, and there comes a stage when it is quite significant. In fact, it is so significant, and there are other effects as well. There is an effect called the hyperfine effect, the hyperfine splitting, which arises due to the coupling between the magnetic moment of the electron and the magnetic moment of the nucleus itself. And that is an even smaller effect, but as z increases, as the atomic number increases, this becomes sufficiently large so that you have significant amount of splitting, and then this neat ordering of these energy levels, the s state and then the p state and then the d state and so on, and that is gone. There could be the f state may be lower in energy than the d state and so on. This happens when you reach the transition metals and is responsible for a lot of interesting effects. But the important point I want to make is that both the spin orbit coupling as well as the effect of an external magnetic field, they all serve to break the symmetry that the original hydrogen atom has, the Coulomb problem has. And so the general lesson is the application of a field breaks symmetry in some sense. After all, the space in this room is isotropic, but all the directions are not equivalent because there is a vertical direction in which there is a gravitational field that breaks the translational symmetry, and that is the reason if you have a particle moving around in this room under the effect of this gravity, the x and y components of its momentum are conserved in the classical picture because there is no force in that direction, but the z component certainly is not. So linear momentum conservation is broken in one direction because of the symmetry breaking field. The gravity acts as such a field. Okay. The next question was, a particle of mass moving in one dimension is incident upon a delta function barrier, not an attractive delta function but a barrier, and the statement was the reflection coefficient of the particle is identically equal to 0. This is certainly not true. We saw explicitly that there is a definite effect of the barrier, even though it is a thin, infinitely thin barrier. The fact is the potential goes to infinity at that point, and therefore there is a finite reflection coefficient. We computed this reflection coefficient as a limiting case of what happens in a rectangular barrier. What you have to do is to take the product of the width of this barrier times the height, retain that to be a finite constant, and then you can compute what it is in the limit. Okay. The only normalizable so this statement is false, the second statement is false. The only normalizable eigenstate of the raising operator A dagger of the linear harmonic oscillator is the ground state of the Hamiltonian. Is this true or false? It is false, because certainly the ground state of the Hamiltonian is not an eigenstate of A dagger, and in fact A dagger has no normalizable eigenstates whatsoever in the space, no eigenstate in the space of square integrable functions. Okay. What about A? What about A?
It has eigenstate.
Does that have eigenstates? Yeah. The ground state of the Hamiltonian also is an eigenstate of A, but then all coherent states are eigenstates of A. Okay. The angular momentum commutation relations Ji, Jj is I h cross. Yeah.
Is it the eigenstates of the?
Yes, I defined oscillator coherent states in that way. Now there are several reasons why we call it a coherent state. I will mention some of these a little later. I am going to talk about coherent states specifically, but right now by a coherent state I mean an eigenstate of the lowering operator A for the harmonic oscillator. So one should really call them harmonic oscillator coherent states, if you like. So I have been careful to do that every now and then. They are also minimum and uncertainty states, as you saw that in suitable units delta x and delta p are each equal to 1 over square root of 2 in this state. That is the minimum possible. They are Gaussian wave packets in the position representation or in the momentum representation, okay. But they are not the ground state of the harmonic oscillator itself, but displaced with respect to the ground state. Okay. there is a way of defining generalized, there are several ways of defining coherent states and they all happen to coincide in this particular instance. The next question was the angular momentum commutation relations together with the requirement that the eigenstates of the angular momentum be normalizable suffice to determine the possible eigenvalues of j squared and j dot n where n is a unit vector along any arbitrary direction. This is true, we saw that this was so, but the important thing is to put in the normalization condition, and that was true even for the harmonic oscillator because I required normalization on the states and that is how I got a discrete spectrum. If you do not require normalizable eigenstates then there is no guarantee that the spectrum is discrete or anything like that. You could have in a more general family of wave function or eigenstates you could have a continuous spectrum for the same operator. So again in these cases given an operator its spectrum is decided by what class of eigenstates you would like to look at, you would like to have for physical reasons. Okay. We want normalizability for conservation of probability and the interpretation of quantum mechanics, but conceivably mathematically there could be more, there could be a continuous spectrum with non-normalizable states. Okay. So that statement was true. A particle moves in one dimension in a symmetric potential V of x is V of minus x, all the energy levels of the particle are discrete, so you are given that you only have bound states, all the wave functions die down exponentially fast at infinity on both sides. The position space wave function of the particle in the ground state phi naught of x is an even function of x, true. In this problem given that the potential is V of x equal to V of minus x, in one dimension there is no degeneracy, everything is a discrete spectrum and there is nothing, no degeneracy, there are no other functionally independent constants of the motion, nothing other than the Hamiltonian, because classically you know that saying the Hamiltonian h of qp equal to constant fixes the phase trajectories, you can't have a second independent constant of the motion functionally. Quantum mechanically it means you cannot have another operator other than the Hamiltonian or some function of the Hamiltonian which commutes with the Hamiltonian. So the levels are non-degenerate, and then if the potential is symmetric the Hamiltonian commutes with the parity operator and therefore you can find a complete set of common eigenstates of the two. Now the parity operator has eigenstates all even functions and all odd functions, but the Hamiltonian has special eigenfunctions and they form a complete set in this space. So the conclusion is every eigenstate of the Hamiltonian is also a parity eigenstate, which means every eigenstate of the Hamiltonian is either an even function of x or an odd function of x in the position space representation. And in the ground state there are no nodes, because every time if you write down the Schrodinger equation, every time the function crosses the axis it has to go up, come down, again go to 0 on both sides, costs energy because there is a second derivative term in this Schrodinger equation. So the lowest energy state would just start off from 0 at minus infinity, it goes up and it comes down and it is normalizable, it has no nodes, and by definition by this requirement that it should be either an even or odd state, since it never crosses the axis it must be an even state. So that is a true statement. Then consider the set of functions phi n of x equal to the oscillator eigenfunctions. This is a normalization constant e to the minus half x squared hn of x, where hn is the Hermite polynomial. Any arbitrary square integrable function of x in minus infinity infinity, this is any L2 function, can be written as a linear combination of the elements of the set in a unique manner. True or false? This is true because this set forms an orthonormal basis, and once it is an orthonormal basis then any function in that space, function space, can be written uniquely. So the coefficients determine the function completely. Okay. What happens if you did not have, suppose for a minute I looked at L2 from 0 to infinity instead of minus infinity to infinity. Let us say we look at the solutions of the 3-dimensional Schrodinger equation and I want the radial part of the wave function. The radial coordinate r, little r, runs from 0 to infinity. You would still require square integrability, so you would now want from 0 to infinity the function mod squared etc. is finite. What would happen in that case? Would the Hermite polynomials form a complete set still? Would they be orthogonal? Do you think so? Would they be a good basis to expand things in? They may not be unique, you think so? First of all, yeah, several physical arguments against it. First of all, we have this weight factor e to the minus half x squared. Hn of x is a polynomial that grows at infinity, but e to the minus half x squared dies down faster than any power, and therefore you are guaranteed that all these polynomials would be integrable when you square it. But if your function, if your variable is going to run from 0 to infinity in x for example, then you do not need e to the minus x squared, e to the minus x would do. You put the x squared because it should be okay at minus infinity too, and I do not want a mod x because that would mean there is a cusp at the origin and so on. So that is one reason why we have e to the minus x squared appearing there naturally, but from 0 to infinity e to the minus x would do. And what do you call that set of functions with the weight factor e to the minus x integrable? They are the Laguerre polynomials. They are in fact the Laguerre polynomials, and that is why that appears in the hydrogen atom problem in a natural way. Okay. Consider a particle with spin quantum number half. The particle can never be in a spin state in which the uncertainty product delta Sx delta Sy is 0. There were mixed results on this question, so let me explain what is happening. We would like to find out what is delta Sx delta Sy in any state, in any arbitrary state. Remember that the uncertainty principle says that this is greater than or equal to 1/2 the modulus of the commutator of Sx with Sy. But this is equal to h cross over 2, this is I h cross Sz times the expectation value of Sz in an arbitrary state. How big can this guy be? No matter what state you are in, that can't be bigger than half, right? Because the eigenstates of Sz, the eigenvalues of Sz would be either plus half or minus half in units of h cross, right? So this is finite, this is a finite quantity. Can it be 0? Yes, of course. Classically you can see that if this is your axis of quantization and you put your spin along the x axis, it is an eigenstate of Sx for example, then the expectation value of Sz is 0, just as when you put it in an eigenstate of Sz, the expectation value of Sx and Sy are 0. In exactly the same way you could have it in a state where the expectation value of this is 0. Classically this would mean the spin quote unquote lies along the in the xy plane, there is no z projection. So the least value of this quantity is in fact 0. So this statement is actually false, it can definitely be in such a state. So you see the significance of this generalized uncertainty principle. So really you should go back to this algebra and say look at it here, and this could be 0. Okay. It can't be negative because the product of uncertainties can never be negative, it could be 0 in some situations. Okay. The functions, again the harmonic oscillator functions, but I have put a tilde and put a p there, otherwise it is exactly the same function as in the position basis, are eigenfunctions of the Fourier transform operator. The answer is yes, they definitely are, because this is the momentum space eigenfunction of the harmonic oscillator. The position space eigenfunction had exactly the same functional form, but we know the momentum space eigenfunction is a Fourier transform of the position space function. Therefore here is a set of functions whose Fourier transforms are essentially constants times the original functions. What can those eigenvalues be? Yeah, the fourth roots of unity, because we know that the fourth power of the Fourier transform operator is the identity operator in this function space. So those functions, those eigenvalues can only be 1, I, minus 1 and minus I, nothing more. The ground state of the oscillator corresponds to eigenvalue 1. That we know follows also from the fact that the Fourier transform of a Gaussian is a Gaussian, and with suitable normalization coefficients it is exactly the same function. Okay. Consider a one dimensional potential barrier V of x, let the reflection and transmission coefficients be R and T. So I have an arbitrary potential barrier and I would like to find out for incidence from here there is a reflection R and there is a transmission T. Now you are asked, suppose you started from there and incidence from there, then there would be a reflection R prime and a transmission T prime, and the question is R equal to R prime and T equal to T prime. Now the way we derived this problem, we derived this expression was simply to say e to the ikx was incident from the right, e to the minus ikx would mean incident from the right, and e to the minus plus ikx would mean going rightwards from the left. The way we derived this entire expression had nothing to do with the directions in which we moved. It was completely arbitrary. All we did was to say that it is a plane wave asymptotically on either side. So in fact the reflection and transmission coefficients are identical. It does not matter which direction you have incidence, and it does not require the symmetry property of the potential because we never use that.
So evaluating the boundary conditions at the when we evaluating the activity of psi and
Still does not matter, still does not matter. So do it for a non-symmetric potential and you will discover that this is exactly the same answer. So do it for a potential which looks like this. Here is a simple potential which would look like this. Do it for a potential of this shape. Okay. It would mean it would mean exactly the same thing. Okay. So this was a little.
potential should become constant at time.
Yeah, we want the potential. We want to make sure the potential vanishes at infinity. So I said there is a finite barrier. This is just a barrier at some point, and it definitely does not mean that the potential extends. If it does, then the energy has to be greater than that value, otherwise you can't even have such a state. So his point is, if the potential were to look like if the potential were to be a barrier like this, you can't have an, and this was a zero of energy, you can't have an energy state below this value. To start with, it has to be above that. Okay. And of course it is easy to see what would happen if you had a lack of symmetry. Suppose you have a V of x looking like this. Now we computed things, because they are analytically computable, we computed things where the potential barrier was actually compact. Beyond a certain stage on either side there was no potential at all, but that is not absolutely essential. You could have a situation like this. This asymptotically goes to 0 and this asymptotes to some finite value here. One could look at this barrier as well. It is just that it is only at minus infinity and plus infinity that you apply these bound plane wave conditions, otherwise it is not necessarily a plane wave at all. The function, eigenfunction can be quite complicated, but for computing R and T you do not need to know the exact potentials, except the formal expressions that you have when you compute the numerical values of the coefficients would depend on the potential. You would need to integrate, you need to solve the Schrdinger equation here. Okay. Let J be the total angular momentum quantum number of a system. Then in any arbitrary state psi of the system, the operator J squared must necessarily have the expectation value h cross squared J times J plus 1. What we are actually saying is, if it has a definite value, then it is an eigenstate of J squared. So we are really saying that an arbitrary state of the system is an eigenstate of the total angular momentum. True or false? It is true, it is true. You have not given any other conditions, so it is certainly true. So the idea is that you have maybe an orbital part, you have other in degrees of freedom, so the total wave function is a product of the spin wave function and the spatial wave function, for instance, and it is always an eigenstate. Just like an electron, no matter what you do to this electron, its spin quantum number is half. Therefore you are guaranteed that if you measure s squared, the answer is going to be 3/4 h cross squared, no matter what you do to the electron. So that is certainly true always. Yeah.
So in the seventh question,
Yeah.
so if we take commutator of Sx and Sy,
Yeah.
we get non-zero value.
Yes.
We get
You get sz.
yeah, we get sigma 3.
Yes, which is sz.
Yeah.
Yes.
So that can't be 0.
No, you can't argue that way. You have to take the expectation value of that operator. So what
So, but
appears
if we
is,
take just commutator of x and p, suppose,
yes,
then we don't take expectation values.
No, you do
of course
take
you do.
expectation. It's
Of course you do.
constant.
But they got a unit operator there, and the expectation value of the unit operator is always 1. That can never be 0. So that's a good point is raised. In the normal commutation relation, in the normal course of events, if you took a Cartesian coordinate delta p, this is certainly greater than or equal to 1/2 the modulus of the expectation value of x with p. That is certainly true, but it so happens that this is equal to IH cross times the unit operator. Therefore this thing here becomes H cross over 2 the modulus of the expectation value of the unit operator, but this guy is by definition 1 no matter what you do. That is the reason you get the usual commutation relation saying it can never be 0, it is greater than or equal to half H cross. But in the spin case this commutator is sz, so what you have to deal with is this quantity, and this could be 0. Okay. So that is the reason it is different from what it is for the usual pair of Cartesian coordinates. Okay. Yeah.
Previous question, will the reflection coefficients be the same even if there are, let's say, two potential?
Yeah, the total reflection coefficients final. We are only talking about minus infinity to infinity, not what happens in an individual barrier. Yeah, that is certainly different. Okay, so I will give a problem where you work this out explicitly and you will see. The next one was fill in the blanks, and the first question was a simple question but was a little bit of a trick. It said a particle moves in a half oscillator potential. I should have made it small m, this became capital M, that was a mistake, but it does not matter. V of x is given to you in any case, half m omega squared x squared and infinity. For x greater than 0 it is the oscillator, for x less than 0 there is a wall. So it is like attaching a spring to one end to the origin, the other end to this particle, letting this particle vibrate but not fully along the x axis, but whenever it hits the x equal to 0 it bounces back. So in this half oscillator potential the question asked is what is the ground state of this problem. So the potential is infinite here, and this is half m omega squared and it is infinite for x less than 0. And now you are asked what is the ground state energy eigenvalue and what are the eigenfunctions. Now you see the earlier problem which you solved, the oscillator problem, had the Hermite polynomials etc., and you used two boundary conditions. At minus and plus infinity the wave function went to 0. Now it is exactly the same differential equation but it applies in the region x greater than 0. So in this region you have this equation minus h cross squared over 2m d2 phi over dx2 plus half m omega squared x squared phi equal to E phi, and this is for x greater than 0. And since the potential is infinite, the wave function is 0 in this region including at this point. So when you solve this and you impose the condition of square integrability that the function be finite at infinity, the energy levels turn out to be discrete as before, the solutions are the Hermite polynomials, but they would be those Hermite polynomials which vanish at the origin. and which ones are those? The odd ones vanish at the origin, the even ones do not vanish at the origin, therefore they can't be solutions to this problem. And what is the lowest odd value, energy value? 3/2 h cross omega. So the spectrum has all the odd eigenvalues only. So the lowest energy value E ground state equal to 3/2 h cross, purely from the boundary condition. So the even ones are not allowed in this case, and it picks out every other one. So by the way, that now is a set that forms a complete set. So only the even ones and the odd ones are sufficient, they form a complete set once again. So if you insist on the weight function e to the minus x squared instead of e to the minus x, then you do not get the full set of Hermite polynomials, but the one you get the ones e to the, provided you impose the boundary condition, you look at the class of functions which vanish at the origin, okay. Then e to the minus x squared times the odd Hermite polynomials form a complete set.
What if the potential is half m omega square in the left hand side and there is a potential value at x?
What kind? Half, so what should I?
Same thing.
Same argument, yeah. Same argument. I mean, this doesn't matter whether it's left or right. I mean, that doesn't matter. Half oscillator, it doesn't matter. That really won't matter at all. Even if the potential were infinite on for x greater than 0 and oscillator for x less than 0, it's exactly the same thing. What happens if the spring constant becomes negative? What happens if the potential is minus half constant times x squared? What would you say? This is your potential. That is your potential. What would be the, can you have bound states in this problem? No, there are no normalizable eigenfunctions of the Hamiltonian, no bound states at all. Classically the origin is an unstable equilibrium point, just falls off from the origin. So corresponding to that, in quantum mechanics there are no bound states. The general lesson is that bound states would correspond to periodic solutions in the classical case. So anything that is periodic becomes a bound state in quantum mechanics. No periodic orbits are allowed here. The next one was the Hamiltonian of a perturbed oscillator is given by the usual h cross omega a dagger a plus half plus lambda times a plus a dagger, and the question is what is the exact value of the ground state. This is just a shifted oscillator. All you have to do is to recognize that you have just shifted the oscillator because a plus a dagger is x, and what you have done is to take p squared plus x squared plus put an x term, so complete squares, it is like shifting the oscillator and changing the 0 of the energy, and all you are asked to find is what is the change in the 0 of the energy. So that is easily found because you have h cross omega a dagger a plus a half plus lambda a plus a dagger. Notice lambda is real and this is a Hermitian quantity, so the Hamiltonian is Hermitian and the eigenstates are eigenvalues are guaranteed to be real. So you could write this as h cross omega times a dagger a plus lambda over h cross omega a plus a dagger. This is the 0 point energy there. Okay. So all you have to do is to define a B equal to A plus lambda over h cross omega. Okay. The commutator, so B dagger is A dagger plus lambda h cross omega once again, and the important thing is the commutator of B with B dagger is still equal to 1, and that is all that decides the spectrum. So this whole thing becomes equal to h cross omega B dagger B plus a half minus lambda over lambda squared over h cross omega. If I complete squares, there is an extra term I have added which is lambda squared over h cross squared omega squared, but there is one sitting outside here, that is it. So what is the ground state energy? This portion has a ground state energy which is half h cross omega. So E ground state equal to h cross omega by 2 minus lambda squared over h cross omega. That is the exact answer. Okay. You just subtract that portion out, that is it. So what has been done by adding this thing is to start with this potential and move to a potential which looks like this. That is all that has happened. It is still a set of eigenvalues, a discrete set, and all we are saying is that what was 0 here has been shifted to minus lambda squared over h. Okay. The next one said, let S be the spin operator of a spin half particle and n prime are two arbitrary directions. Then you ask to find the commutator s dot n prime, and remember that we have relations for the Pauli matrices. So s dot n prime, this is equal to h cross squared over 4, because S involves is h cross over 2 times the Pauli matrix, and then the commutator of sigma dot n with sigma dot n prime. Okay. That is equal to, what is this commutator equal to, and that has been given to you, right. It is 2i n cross n prime in that order. So this is equal to h cross squared over 2i n cross n prime dot sigma. Okay. It has got to be an operator at the end. This is a commutator of 2 operators, so there has to be a sigma. It is equal to this. Okay. You can re-express it in terms of S if you like. So h cross over 2 is this. So it is now up and down are the usual eigenstates, and you are asked what is the operator Sx Sy in this basis. Well, it is just a simple trivial exercise understanding what is meant by the basis. So we know that Sx Sy equal to h cross squared over 4 sigma x sigma y, but sigma x sigma y is I sigma z, which is equal to I h cross over 2 sz. We know that. Okay. So you can retain it either in this form or in that form, it does not matter really. Then what is this matrix equal to? As a matrix, this is equal to h cross squared over 4 I here, and then a 1 0 0 minus 1, that is it. So as an operator, remember this is in the basis in which you have diagonalized along Sz itself. So as an operator it says Sx Sy is equal to I h cross squared over 4, and this basis it is this guy here up, and then the minus sign, so minus, it is a diagonal operator. So the one with the ket up bra down, the ket down and bra up does not appear at all, these elements are 0, and this minus sign takes care of this minus sign here, that is it. Okay. Then in the state cos theta e to the minus I phi sin half theta, the expectation value of Sx plus I Sy. Once again you just have to write the representation for these guys. And you have to compute a simple matrix element. By the way, what is Sx plus Isy? Is h cross over 2, and it is equal to sigma x plus I sigma y. This is 0 here, sigma y has minus I on top, so it becomes 2, and then it has 0 and a 0, which is h cross times 0 1 0 0, and then the expectation value of this quantity is equal to, in this state, given this state, so this state is cos theta over 2 e to the I phi. Complex conjugate is needed when you take the bra, you got to be careful, that is the only place you have to be a little careful, this times, so it is h cross 0 1 0 0 on cos theta over 2 that is it. So you just have to carry out this trivial multiplication. So what do you get? You get so multiplying this, you get 0 here, and you get e to the minus I phi sin theta over 2 and a 0. So this is equal to h cross over 2 e to the minus I phi sin theta, because cos theta over 2 sin theta over 2 multiply by 2 and divide, and that is the sin theta, that is it. So that is the answer. Now of course you should check, if theta is 0, where are you then? You are in an eigenstate of Sz itself, and then I know the expectation value of Sx and Sy are both 0. So you should check if theta is 0 that this is true, and that is certainly true, vanishes at theta equal to 0. Alright, the degeneracy of an electron we have already talked about, and then the formal solution to the Schrodinger equation for a free particle, we have asked for the propagator here. What do you think it is? Recall I had already given the answer for an harmonic oscillator, and if you set omega equal to 0, then you get the answer for the free propagator, and that has combinations like an omega on top and a sin omega t below, and as omega goes to 0, sin x over x goes to 1, or sin ax over x goes to a. So you need to use that fact. Even otherwise you could write this down, but the free particle propagator would be something like m over 2 pi I h cross t. I do not swear to this, but it is something of this kind, exponential of minus x prime whole squared minus m over 2 I h cross t, and this is equal to k of x prime t. I just wrote this down because I remember the solution to the diffusion equation, and I know that two whatever it is, what is it, I h cross over 2m is the diffusion coefficient for the Schrodinger equation. Okay. So this is the yeah. Yes.
As e power minus I h by h cross t,
yes,
times psi of x comma 0.
Yes.
And write psi of x comma 0 as integral minus infinity of delta of x minus x prime times psi of x prime comma 0.
Okay.
Can we compare this and get,
yes.
Okay.
But how are you going to exponentiate it? The point is, how are you going to exponentiate it? You found this by actually solving this equation. So the statement is, if you write delta psi over delta t, I h cross this is minus h cross squared over 2m d2 over dx2 psi, then regarded as a function of t alone, this is a first order differential equation, and this quantity is an operator in x but not in t. So in a sense, psi of x at time t is this exponential of this operator acting on psi of x at time 0, but the exponential of that operator is an integral operator. So when you explicitly write it out, although formally you can write it in this form, explicitly when you write it out you get an integral operator with some kernel, and that is the kernel out there. You see. just as if I write e to the power a d over dx on f of x, this is not a local operator. Even though d over dx is a local operator, at each point you find the derivative. This is not a local operator because all powers of this derivative are involved here when you do the expansion of the exponential. Therefore, this, as we know, is actually equal to f of x plus a. So it is a translation operator. In exactly the same way, it turns out e to the power some b d2 over dx2 on f of x cannot be written as something which depends on x alone. It is not a local operator, just as this depends on x plus a, it is at a finite distance away. In this case, it turns out this can only be written as an integral from minus infinity to infinity dx prime acting on f of x prime, but what acts on it is a kernel x comma x prime, and this kernel here is of the form e to the minus x prime whole squared over something which involves b and so on. So it is a non-local quantity and should not be too surprising, because if I have a function at some point here, if I specify this the value of this x axis, you know what the function's value is, right. If I specify the abscissa, you know the ordinate. Now if I differentiate this function, then I need to know the value of the function at two neighboring points so that I can take the slope. If I would like to find the curvature at that point, slope is not enough, I need to take the second difference. That means I go a little further and take the difference of the differences and so on. So in a sense, to go a finite distance, you need an infinite number of derivatives, and that is what is happening here too. The infinite number of all powers, all derivatives are involved. So it is not surprising that the value of this quantity depends on the function everywhere else throughout, with that weight factor, with that kernel. So the answer is definitely a function of x finally, but it would be a function of x depending on everything else, and that is what has happened here. So what we found here is the solution to this equation, explicit solution to this equation, which you can find in many ways, but this quantity is a propagator. It has the advantage that now if you give me an arbitrary initial function and not a delta function, or say that the function is 0 everywhere except at one point or anything like that, I can still find the solution. Okay. So the formal solution to this guy, once I put that in, then I know that psi of x comma t is an integral k of x prime t dx prime psi of x prime 0. So this is the initial value. So you converted this, it is an initial value problem. So given the initial probability amplitude, I am able to find the probability amplitude at all later times with this propagator that takes me from the initial to the final state. Okay. So I guess we are almost done. The last one was the action of J plus on Jm. This is something we already worked out. This is equal to square. It must vanish when m equal to j. So that is our mnemonic device. It says j minus m, and then it is j plus m plus 1. It is the raising operator, so it takes j and converts it jm and makes it m plus 1. Okay. Had you had j minus here, this would be j plus m, and that would be j minus m, and this would be m minus 1. It lowers it by 1. Okay. The equation of motion satisfied by the expectation value of the position of a particle when it is an eigenstate of the momentum operator with eigenvalue p is. Now I did not ask for the solution, I asked for the equation of motion, okay, and the equation of motion is a classical equation of motion. So it just says d over dt of r equal to p over m. That is the equation of motion. Of course if you solve it, then you need to know what our expectation of r is at t equal to 0, and it is equal to that plus whatever it is. Okay. So this is the equation of motion. It follows from Heisenberg's equation of motion. For a free particle the Hamiltonian is p squared over 2m, so dp over dt is 1 over I h cross, the commutator of p with h, that is it. Okay. For r with h. Okay. All right. The expectation value of A dagger A in the coherent state alpha of the linear harmonic oscillator is, and this tells us the physical meaning, one of the meanings of this complex number alpha, which is the eigenstate of A, and the expectation value is not hard to find. Remember that the coherent state alpha was defined as e to the minus mod alpha squared summation n equal to 0 to infinity alpha to the n over square root of n factorial acting on n. You could now ask what is A dagger A acting on this and find with an alpha on the left hand side. So alpha A dagger A alpha equal to e to the minus mod alpha squared, because you are going to multiply two of these fellows here, and then a summation n equal to 0 to infinity alpha to the n alpha star to the n, because this would have been m on the left, but I am going to use the orthonormality condition, so it becomes alpha star on this side divided by n factorial, because you can't do square root of n factorial, you can't sum, but n factorial in the denominator is easy, and then you put an alpha A dagger A, when it acts on n it just produces an n times n, and of course this is mod alpha squared to the power n. Okay. This sum is easy to do, you start from n equal to 1 onwards, n equal to 0 is 0 by definition because of this guy here, and this series is equal to mod alpha squared. Yeah. Absolutely. Absolutely. That is it. Even more trivially. Thank you. That is exactly right. So if you put beta equal to A on alpha, which incidentally is alpha on alpha, then this quantity here is nothing but norm of beta on beta equal to mod alpha squared. Okay. Absolutely. Yeah. So this is the meaning of mod alpha squared. It is in fact the expectation value of the number of quanta. If we regard this as the state of the radiation field, it is the number of photons in a coherent state, the average value of the number of photons, because you are not in a number state, you are not in an eigenstate of A dagger A, but in a superposition of these states, and therefore there is some average value, and that is mod alpha squared in this problem. Now what are the allowed values of mod alpha squared? That is it, 0 to infinity, 0 to infinity. It is 0 if and only if alpha is 0, and when alpha is 0, then the state that you get is in fact the ground state of the harmonic oscillator, in which the expectation value of n is 0 anyway, it is the vacuum state for the radiation field. Okay. Otherwise you get the finite number here. Okay. Now of course you can also generate this, you could also have written this as e to the minus half mod alpha squared e to the power, you can write this as equal to A dagger to the n over square root of n factorial on 0, in which case you get e to the power alpha A dagger on 0. The advantage of this is there is no summation, it tells you that some operator acting on the ground state produces this coherent state, but an even better way of writing this is by using this Adamar lemma, the commutation relations. You can also write this as e to the alpha A dagger minus alpha star A acting on 0. That is a very, very important way of writing it. This thing is called the displacement operator d of alpha, it is a function of alpha and alpha star, but I will just omit the alpha star there. okay. It is a unitary operator. So in a sense a coherent state is a unitary transformation on the ground state of the harmonic oscillator, and this unitary transformation is parameterized by a complex number. Therefore the natural question to ask is, what is this really telling you? Well, this set of unitary transformations forms a group, and there is a group multiplication law which says d of alpha d of beta is d of alpha plus beta times a phase factor, okay. And this is this whole thing is a representation of the original, it is called the Weil group, okay. Because after all A and A dagger form A dagger and the unit operator form the Heisenberg algebra, and you have now exponentiated these operators. We will come back to this because they play a significant role in quantum optics, so we will come back and discuss this. So let me stop here today.